So how do we identify this second threshold point, the lactate turn point, LT2? Well, the first approach we're going to look at is perhaps the most widely used method globally, which is the idea of doing a visual inspection of the blood lactate profile. And it's kind of summarised a little bit in this paper from Newland colleagues back in 2007. Traditionally, the lactate threshold, gosh, it gets confusing. They mean LT2. So remember, they just mean the kick. It's just the terminology. They mean the transition from moderate to heavy was determined subjectively from plots of the lactate concentration versus work rate by visually identifying the treadmill velocity or work rate that best corresponds to a departure from linear baseline pattern, and that is in lactate. So what you would get is something like this. Now this is nice because you can see this really clear in this data. So this is data published by Andy Jones and Helen Carter. And what they've got data here is data pre and post training. And you can see visually where the response occurs. So you can see quite clearly that the transition occurs here. So this is 11 kilometers an hour, and I can see that the transition where you get this, these are the steady state response in both conditions, and then you start to go into this form of steady state. This is into the heavy domain response. So you can see that sudden acceleration of the blood lactate profile. So it's really obvious and really clear to see. But what happens if it's not so clear? That certainly will complicate the issues for us. So this is data from another paper we published. This is in Swimmers, and it shows us two things really. One, it shows us the difficulty in assessing swimmers, which is highlighted by the error bars which are on the x-axis, and showing that kind of despite the fact you're asking them to swim to pace, it's really difficult. But it's also almost impossible, and this is group-based data to a certain degree, it does confound us a little bit, but it's almost impossible to see a significant transition on either of these curves that represents an obvious acceleration in the blood lactate concentration. So how do we kind of get around that? Well, one of the ways that you may want to deal with this is rather than just doing straight visual inspection, you may just look at the responses in terms of the data. So look at the actual data that's been produced and calculate the delta blood lactate responses. So what is the change in the blood lactate concentration? And use the change in the blood lactate concentration where you find the first significant big change as your proxy indicator of LT2. But it's worth bearing in mind that this is not, an issue that is new or current. There was some work published in the 80s by Ye and colleagues, and what they did was they provided exercise physiologists with blank plots which simply showed the lactate concentration against workload, and they asked the physiologists, renowned physiologists, to identify LT2, and there was no agreement at all. No agreement. Nobody could agree. Now that's problematic. If you can't get physiologists to agree when they're doing a visual inspection, how are coaches or less experienced physiologists able to make that agreement and identify this point precisely? The second thing to really think about here is this is it feels very unscientific. It's quite subjective, isn't it? It's to a certain degree, well, I think it's this point here. And the final thing really to think about here with visual inspection is if you look at this plot, you can see that issue that I was talking about, which is this is data taken from our laboratory, is that it's not obvious where the transition is. Is the transition here? Is it here? Is it here? Where's the first acceleration take place? And so you kind of get into that quandary about, well, is it kind of speculation? And then you get into the issue, which is a real big issue and a real concern, which is going to be relevant to everything we refer to today, which is how do you know that the LT2 is at 210 watts, as an example? Why isn't it at 215 or 230 watts? Because if you were to put something like a polynomial curve through this, the polynomial may predict that it's actually somewhere in here. Now, this is where you get down to issues of understanding in terms of working with things like curve fitting. All curve fitting is doing is predicting. It's predicting what that lactate response would be. It's not representative of what the lactate response actually would be. And this is why you'll notice there is no line in here to connect the points, because we don't know what the lactate concentration is doing between each of these workloads. Now, a mathematician would argue, well, that's the whole point of curve fitting. It's kind of meant to represent that response. But because there is so much inherent variability in blood lactate data, because of where you take the sample from, if you change the sample point, so you've cleaned the finger between samples, you may end up not taking it from the same wound that you've created. You may hit different capillaries, you may hit an arterial orientated capillary as opposed to a venous orientated capillary. It will change the lactate concentration. So the curve is only as good as the data which it's being provided with, and if we get inherent variability in the data, the identification of any workload, a predicted workload between data points is perhaps slightly spurious. So we do need to be really cautious, but I think it really offers us a problem, which is visual inspection is subjective. It is not really representative of a scientific method for identifying what is fundamentally a really important and crucial point. And indeed, when we look at this is quite nice data. This is using Bland-Altman plots. And what they've done is they've looked at the test-retest on the lactate turn point. And so they've done it in males and females. And what you have to understand with Bland-Altman plots, so what they give you is, this is the 0 line. So we have 3 additional lines here. So this represents what's called the bias score, which is the mean of the differences. And these are the 95% confidence intervals. So fundamentally, these represent the spread of the data. So when we're talking about test-retest reliability, 2 things that exist. One, the closer the data is to the bias line, the better. And of course, fundamentally, the smaller the gap between the confidence intervals, the better. And we want all the data really to be sitting inside those confidence intervals. So when we look at this, the plus or minus, okay, in terms of the speed at which the turn point occurred at, has got a difference here of, it goes to -1, well, we'll call that -1.2 to probably 1.5. So the difference here is amazingly, is a 2.7 variability in running speed. That's a very, very big difference. So there seems to be an issue here in test-retest reliability. Now, the question to ask yourself is that a reliability measure of the protocol, or is it a reliability measure of the athlete? And it's difficult to ascertain that from this kind of analysis. But it certainly indicates that there was issues potentially in identification. This is using visual inspection of the lactate turn point.